The UFER ground terminates at the point of its emergence from the concrete footer. Upon exiting the footer, its designation transitions from a grounding electrode to a grounding conductor. Consequently, adhering to electrical code standards, a non-reversible connection is mandated for linking it to the grounding electrode conductor. Let's delve into the specifics. A UFER ground, also known as a concrete encased electrode, is a grounding electrode that is encased in concrete. Typically, it consists of at least 20 feet of bare copper conductor, size no smaller than number 4 AWG, encased within at least 2 inches of concrete that is in direct contact with the earth. Its primary purpose is to provide a low impedance path for fault current to return to the source, thereby facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. The National Electrical Code, or NEC, outlines the requirements for grounding and bonding in electrical systems. Grounding ensures a low impedance path for fault current, protecting people and equipment from electrical shock and damage. A grounding electrode system consists of various electrodes such as ground rods, ground plates, metal underground water pipes, and concrete encased electrodes like the UFER ground. When the UFER ground is encased within the concrete footer, it functions as a grounding electrode. It is an integral part of the grounding electrode system and contributes to the overall effectiveness of the grounding system. However, the moment the conductor exits the concrete footer, it ceases to be a grounding electrode in the strict sense. It transitions into a grounding conductor. Grounding conductors are used to connect grounding electrodes to the electrical system's grounding bus or terminal. They serve as the pathway for fault current to travel from the electrical system back to the grounding electrode. Because the section of conductor emerging from the footer serves the function of connecting the grounding electrode, the UFER, to the rest of the grounding system, it is treated as a grounding conductor. Now let's discuss the connection requirements. Given its new designation as a grounding conductor, the connection of the emerging conductor to the grounding electrode conductor, or GEC, must comply with specific NEC requirements. The NEC mandates the use of a non-reversible connection method. A non-reversible connection is one that is mechanically and electrically sound, and is designed to prevent accidental loosening or disconnection. Examples of non-reversible connections include exothermic wells, reversible compression connectors, and appropriately listed and labeled bolted connections. The purpose of requiring a non-reversible connection is to ensure the long-term reliability and integrity of the grounding system. A loose or corroded connection can significantly increase the impedance of the grounding path, thereby diminishing its effectiveness and clearing ground faults. Using a common split-bolt connector, often informally referred to as a BOG, might seem convenient, however it generally does not meet the NEC requirements for a non-reversible connection for grounding electrode conductors unless it is specifically listed and labeled for that purpose. The NEC stipulates that connections to grounding electrodes and grounding electrode conductors must be made using methods that are listed and labeled for the purpose. Listed and labeled means that the connection method has been tested and certified by a recognized testing laboratory to meet specific performance standards. When selecting a connection method, it's essential to verify that it is explicitly listed and labeled for grounding applications and that it is suitable for the specific conductor materials and sizes being used. Exothermic welding, also known as a CAD weld, is a process that creates a permanent metallurgical bond between conductors. It involves using a mold to contain the conductors and then igniting a special welding compound within the mold. The resulting chemical reaction generates intense heat, which melts the conductors together, forming a solid, homogeneous connection. Exothermic welds are highly reliable and resistant to corrosion, making them an excellent choice for grounding electrode conductor connections. Irreversible compression connectors are another acceptable method. These connectors are installed using a specialized crimping tool that applies high pressure to create a permanent mechanical and electrical connection. The connector is designed to deform during the crimping process, ensuring a tight and secure fit. Irreversible compression connectors are available in various sizes and materials to accommodate different conductor types and sizes. Bolted connections can be used, provided that they are listed and labeled for grounding applications and are properly installed. The hardware used for bolted connections, such as bolts, nuts, and washers, must be made of corrosion-resistant materials, such as stainless steel or bronze. The connection surfaces must be clean and free of any contaminants that could impede electrical conductivity. The bolts must be tightened to the manufacturer's specified torque to ensure a secure and reliable connection. Some additional considerations are also worthy of discussion. The size of the grounding electrode conductor must be selected in accordance with NEC Table 250.66. The size of the GEC is based on the size of the largest unrounded surface entrance conductor or equivalent area for parallel conductors. The GEC must be adequately sized to safely carry the maximum available fault current. It is important to protect the grounding electrode conductor from physical damage. If the GEC is exposed to physical damage, it must be protected by conduit, armor, or other suitable means. This is especially important in areas where the GEC could be subjected to impact or abrasion. The grounding electrode conductor must be run in a straight line as much as is practical. Avoid sharp bends or kinks in the conductor, as these can increase impedance and reduce the effectiveness of the grounding system. The grounding electrode conductor should be readily accessible for inspection and maintenance. Avoid burying the conductor in locations where it would be difficult to access. Regularly inspect the grounding electrode conductor and its connections for signs of corrosion or damage. Any damaged or corroded component should be replaced immediately. In summary, the UFER ground ceases to be a grounding electrode upon exiting the concrete footer and becomes a grounding conductor. A non-reversible connection, such as an exothermic weld, reversible compression connector, or listed and labeled bolted connection, is required to connect it to the grounding electrode conductor. Adhering to these requirements ensures a safe and effective grounding system, protecting people and equipment from electrical hazards. The transition point of a UFER ground from electrode to conductor is vital for ensuring electrical safety and code compliance. The NEC provides specific guidelines to ensure proper grounding and bonding practices. Grounding systems are designed to provide a low impedance path for fault currents, protecting individuals and equipment from electrical shock and damage. The UFER ground, when encased in concrete, serves as an effective grounding electrode due to its large surface area in contact with the earth. This large surface area provides a low resistance path for fault currents to dissipate into the earth. Once the UFER ground emerges from the concrete footer, it no longer functions as a grounding electrode but rather as a grounding conductor. Grounding conductors connect grounding electrodes to the electrical system's grounding bus or terminal. The NEC mandates the use of non-reversible connections for grounding electrode conductors to ensure a permanent and reliable connection. Non-reversible connections include exothermic welding, irreversible compression connectors, and listed bolted connections. These connections are designed to withstand mechanical stress, corrosion, and other environmental factors that could compromise the integrity of the grounding system. Exothermic welding, also known as a CAD weld connection, creates a molecular bond between the grounding electrode conductor and the grounding electrode. This type of connection provides a low-resistance, corrosion-resistant pathway for fault currents. Irreversible compression connectors use specialized crimping tools to create a permanent mechanical and electrical connection. These connectors are designed to deform during the crimping process, ensuring a tight and secure fit. Listed bolted connections are permitted if they are specifically listed for grounding applications and installed according to the manufacturer's instructions. All hardware used in bolted connections must be corrosion resistant and properly torqued to maintain a secure connection. It is essential to select the appropriate size grounding electrode conductor based on the size of the service entrance conductors, as specified in NEC Table 250.66. The grounding electrode conductor must be protected from physical damage to ensure its long-term reliability. If the grounding electrode conductor is exposed to physical damage, it must be protected by conduit, enclosures, or other suitable means. The grounding electrode conductor should be installed in a straight line as much as possible to minimize impedance. Sharp bends and kinks can increase impedance and reduce the effectiveness of the grounding system. Regular inspections of the grounding electrode conductor and its connections are essential to identify any signs of corrosion, damage, or loose connections. Any damaged or corroded component should be replaced immediately to maintain the integrity of the grounding system. Proper grounding practices are crucial for electrical safety and code compliance. Understanding the transition point of a UFER ground from electrode to conductor and the requirements for non-reversible connections is essential for ensuring a safe and reliable electrical system. By following the guidelines outlined in the NEC and using appropriate connection methods, electrical professionals can effectively protect people and equipment from electrical hazards. The UFER ground system offers a robust and reliable method for grounding electrical systems, especially when properly installed and maintained. Its effectiveness relies on the proper transition from the concrete encased electrode to the grounding conductor, and the adherence to NEC guidelines for connections and conductor sizing. In addition to ensuring personal safety and equipment protection, a well-maintained grounding system also contributes to the overall performance and reliability of the electrical system. By providing a low impedance path for fault currents, the grounding system helps to minimize voltage fluctuations and prevent equipment malfunctions. The selection of appropriate grounding methods and materials is crucial for ensuring the long-term performance of the grounding system. Factors such as soil conditions, environmental factors, and the type of electrical equipment being grounded should be considered when designing and installing a grounding system. Consulting with a qualified electrical engineer or contractor is recommended to ensure that the grounding system meets the specific requirements of the application and complies with all applicable codes and standards. Regular training and education on grounding and bonding practices are essential for electrical professionals to stay up to date on the latest requirements and best practices. The NEC is updated every 3 years, and it is important to stay informed of any changes that may affect grounding and bonding requirements. By investing in training and education, electrical professionals can enhance their knowledge and skills and provide their clients with the highest level of electrical safety and service. Remember to always consult the latest edition of the NEC and local codes for specific requirements and regulations related to grounding and bonding.